Hi, I'd like to talk to you about enzymes. Okay, continuing on with Unit B, models of enzyme activity. We already talked about this in the first section. Is lock and key model. We sort of talked about it. So lock and key is the older model, and it's basically that in that model everything is rigid. I can't use this. Everything is rigid. So pretend that this hat is rigid. So my head is the substrate and this hat is the enzyme, and they are perfectly shaped for each other in a lock and key model. And they just fit together perfectly. The hat does something to my head. It cleaves my head or does whatever it is that it does. My head is changed or cut in half or synthesized or put together, and the hat floats off. In an induced fit hypothesis, the things aren't perfect, and this is more true to life, this model. So basically, when the enzyme and the substrate fit together, they change shape. So as you can see here, the hat changes shape just a little bit to meet my head. My head gets pressed in a little bit, and when that happens, that movement, that change of shape is actually what then starts the action, whatever the hat is going to do, whatever the enzyme is going to do to my head. I don't know, remove more hair or whatever it is, cleave the hair off my head. Because very little biology is rigid. Biological systems are squishy or gushy, mushy. So that is a more true to life system. So instead of, and I don't know why we mentioned this, but it's mentioned mentioned in the curriculum. So here it is. I don't know why we talk about the lock and key model. I guess the lock and key, when there's an inhibitor, that works really well for the lock and key. Okay, anyways, so I've talked about that. Next thing. Apoenzyme and holoenzyme. So enzymes, they are they're those amino acids we're talking about. There's those amino acid chains, and when an enzyme is just an amino acid chain, it isn't always just an amino acid chain, but when it's just the amino acid chain, that's the pure protein content with those hydrogen bonds kind of holding it. That's called an apoenzyme. Apoenzyme. I'm always terrible with pronunciation. And then what happens is a cofactor has to come in to activate the enzyme. And the cofactor attaches somewhere on the enzyme, so it changes shape, and now it's the right shape, and it can attach itself to the substrate. Before that, the active site is the wrong shape for the substrate. It can't do its thing. The cofactor comes in, and now it can do its thing. I don't know, if this is a cofactor, it comes in, and now this pen thing is in here, and now we're ready. It has some, let's say it has some negative charge on here. It rearranges things so this positive thing or this negative thing has moved away, and now the enzyme is open and ready for action, ready to take in a substrate and do its thing. And that the complex, when the cofactor and the enzyme are together, that's called a holoenzyme. It's called a holoenzyme. And there's two types of cofactors. There are metal ion activators. Potassium, zinc are examples. That's why you're supposed to take zinc supplements. All the health places say take zinc supplements because it helps your enzymes. It helps your metabolic enzymes. Yeah, technically, yeah, sure, okay. Potassium, same thing with potassium, right? All that, and there's a whole bunch of other enzymes. And then there's coenzymes, another big, huge industry, vitamins. Whether or not, studies have been somewhat inconclusive, although, you know what, don't quote me on that because I haven't really looked into it, so. Whether taking vitamin supplements, I don't know. I hear around the Kapinski household, there's lots of vitamin C. They got a lot of vitamin C. No one wants to get sick all the time. We have those little packets. Well, right, we use them all up. Anyways, I don't know if it's good. Whatever. It makes you feel psychological. If it doesn't work, it's good. It's fine. So there's two types of coenzymes. Like I said, the metal there's the two types of cofactors, metal ion activators, and there's coenzymes. And coenzymes are non-organic kind of complexes. They're derived from vitamins. They're non-organic molecules. And they help create the active site the same way. They attach somewhere on the enzyme, and basically they're taking up electrons. They're changing the electron, right? You got the hydrogen bonds and stuff. Hydrogen bonds are like, when you learned about water in A, hopefully, you learned, water has the big oxygen end and the two hydrogen ends, and the hydrogen ends are positively charged. The oxygen end is negatively charged, and so that's why water is so interesting, because the negative ends of the negative and the positive end of two water molecules, they attach together and they form this complex. That's called a hydrogen bond here. The hydrogen and the oxygen bit are making a hydrogen bond, and then there's a hydrogen bond over here and a hydrogen bond over here. That's why water can stay liquid for such a long time, and it can absorb all that heat. Well, the same thing in enzymes, right? You get hydrogen bonds too, because the R groups, there's negative R groups, positive R groups, you get these hydrogen bonds. And all these hydrogen bonds are really just electrons. It's electron sharing. That's what chemistry is. It's electron sharing. So when you get something like a metal ion that has like a big positive charge coming in there, it's going to start picking up electrons. It's going to start doing things. The same thing with coenzymes. They come along, these molecules, so they're bigger molecules that have a positive charge or whatever, and they redistribute electrons. And when that happens, when electrons get redistributed, it's like the magnetism of the enzyme, basically, because electromagnetism is a thing. It changes, so the enzymes, the active site changes shape, and it turns into the appropriate shape. Factors activity affecting the activity of enzymes. So there's optimum conditions that enzymes function in the human body, for example. That's going to be 37 degrees, around 37 degrees centigrade. It's a little bit different for every person. That's actually might not be your optimum, but 37 degrees centigrade. As the temperature goes up, for example, from 37 degrees centigrade, what does that mean? The temperature is going up. It means energy is feeding into the system. Things are starting to vibrate more. So actually, energy going up might be good, might be the substrate is hitting things, but only for a short time, because then what happens, those hydrogen bonds now, there's energy going into those hydrogen bonds. And just like with water boiling, starting to boil, right? You feed heat into the system. Those hydrogen bonds are absorbing that energy, Finally, they're like, we gotta let go. We got too much energy. And they let go, and water turns into steam. The same thing with enzymes. Those hydrogen bonds, that tertiary structure, there's too much energy, and those hydrogen bonds start to break apart. They start to go too far apart, and the enzyme starts to denature. It starts to just become a long chain of amino acids, and then it doesn't work, because the active site is where all this stuff happens. So what you see in the graph, I put two graphs in the notes. There's a graph, the temperature goes up and things are going up, and then there's kind of a sharp drop off at 37 degrees centigrade. That sharp drop off is because the enzymes are starting to denature. The enzymes stop working. pH is also another place, because what is pH? What is acidity? It's hydrogen ions floating around. The more hydrogen ions you have, the lower your pH, the more acidic your thing is. Those hydrogen ions are positively charged. So there's floating around, there's all this positive charge going around. It's starting to mess with our hydrogen bonds, and the enzymes they kind of don't work. So, but it's a more gradual, there's a graph on there somewhere. So there's an optimum pH. So, and that's dependent on the R groups, what the optimum pH is, and actually kind of what the optimum temperature is. Because some archaea bacteria work at really high temperatures. That's their optimum temperature. It's like super duper hot, 80 degrees centigrade, 120 degrees centigrade, whatever it is. And pH also can vary, right? Pepsin is an enzyme that works in your gut. We're going to talk about it, hopefully, if we ever get to the digestive system. And it works in like pH of 2 to break down, what does it break down? Starch? I think it breaks down, pepsin breaks down, or proteins. No, it breaks down proteins. And then your intestines are more basic, and there's a trypsin or something like that also breaks down proteins. I may be all wrong. I haven't looked at the digestive thing. Well, I did actually. I was looking at it recently, but I forget things instantly. That's why, I feel bad for you. I'm old. I'm allowed to forget stuff. So there, yeah, pH. And so there's these optimum conditions when when it gets too cold though, the enzymes don't denature. And actually when things cool down, if things haven't been burned, then those hydrogen bonds will reform and the enzymes will start working again. They may get damaged. If it gets too hot, they may get damaged and they may not come back. They may be toast. When it's cold, all that happens when it's cold is the things start to actually shrink and become rigid. And also sluggish, right? So the substrate isn't moving around with enough energy now maybe to meet the enzyme and to do the thing. So that's when cold, things start to slow down. And when you heat up, it will, again, speed back up. Interesting thing, so if you want people to hibernate for like space voyages, making them cold is not going to kill them. It will slow down their metabolism. Totally. It will, and they will live in a frozen state. In fact, this is something that medicine do. They freeze people. They bring their bodies down to a cold temperature. Not frozen like for a long distance voyage to Mars or whatever, to Jupiter. But my friend, for example, when he's a young man, he was like 35 or something like that, and he was at the airport in Los Angeles, California, and he was, I think, at the desk renting a car, and all of a sudden he dropped down on the ground with no heartbeat because he had some congenital heart defect that nobody knew about, and his heart stopped. Luckily, it was in an airport. There's defibrillators, there's ambulance, everything was there. They picked him up. They took him to Johns Hopkins Medical Center, the place for cardiac medicine, and they froze him because they didn't know what was wrong with his heart. And they were like, well, we don't know what's wrong with his heart. Something's wrong. I mean, they got his heart pumping again, but they didn't know why. They got it pumping and then it would go all crazy and they had to jumpstart him again. And so they froze him until they could figure out what was wrong with him so he wouldn't die. So he was in like basically like a body bag, grim, like a black rubber body bag that had freezing water running through it. He was also knocked out, obviously, because it would be horribly painful. But the thing is that what kills you when you freeze somebody, really freeze somebody, isn't that the enzymes stop and all the metabolic processes stop. It's that icicles form. And water, right, when it freezes, you're full of water. When it freezes, the molecules actually become bigger because of the way, here they're fitting together when they're liquid, and when they freeze, I can't remember what they do, but they arrange themselves in like a crystal pattern like this. And so their volume gets way bigger. And so, you might have had, I don't know if you've ever put like a Coke bottle in the freezer because you wanted it to get cold faster, and then it burst in the freezer because you forgot about it. Well, that's what happens to all your cells when you freeze. Hyperthermia is when body temperature rises above 37 degrees centigrade. And things are going to start breaking down. Your body's like, hey, let's go into a state of hyperthermia so that it's part of homeostasis. Try to return us back to that 37 degree centigrade temperature. So your capillaries open up, all the blood gets pumped to your capillaries and your extremities. Your hands go red when you're hot, right? Your face turns red when you're all hot, because your body's pumping blood to the surface. It's trying to get to the surface, to the skin, so the heat can exchange with the outside air. Maybe you're sweating too, so that water floating away, evaporating, takes the heat energy and turns it into kinetic energy, and it cools you down. Hypothermia is when you get really cold. It's the other way, and your body starts to shiver to try to give you more kinetic energy, things rubbing together, creating temperature that way. And that's all I really need to say about that. Blood is kept away from the skin, and actually, so blood gets pulled away from your skin and it goes to the vital organs. That's why you get like frostbite, because what happens is that now there's no blood warming your extremities because your body's like, we got to protect the heart and lungs no matter what. Those things keep us going. The brain and the heart and lungs keep those. So all the blood, the warmth of the blood is just going to your brain and your heart and lungs. And the blood starts to drain away from your fingers and your toes, so they start to freeze, and they actually start to freeze, and you get those ice crystals, cells start to burst, and now these cells are dying. They turn black and gross and dead and break off your finger and throw it in the ground. Inhibitors, enzyme inhibitors. So inhibitors are just things that stop the enzyme from working. Am I still recording or am I just talking to nothing? I'm still recording. Good. So they stop things from working. This is so much stuff in one go. Watch, I don't know, break this video up. I should break it up, but how much of this do we have? Oh, we have an endless amount. Oh my God. I should stop it at some point. Okay, I'm gonna stop it here. I'll make another video for inhibitors.